Alright, this is probably the most popular request that I got was number 28, so there should be a number of you watching out for this one. So this is a bacteria problem, and actually it really goes back to Algebra 2. This isn't a calculus topic per se, so I'm going to call upon your understanding of Algebra 2 to understand this one. I'm going to define a few things up front for you that come out of the equation. Don't be distracted by this y prime equals ky. That's really the last thing we're going to be using. What we are told is that y is going to represent the population of the bacteria. We know that k is some constant multiplier that we're trying to find. We're going to have some initial value. We're going to call it a in this particular problem. And initial values occur when time is equal to 0. So we're going to be looking at an initial value at t equals 0, which means that we should also have a variable t for time. So going back to Algebra 2, I think you guys did some work with exponential growth and exponential decay. So hopefully this will look familiar to you. So let me just write this equation down. And this is going to be an e-based equation. It's easiest to work in calculus with exponential function e rather than, base 10 or base 2. But you probably used base 10 back in Algebra 2. So if you replace the e with a 10, maybe that looks a little bit more familiar to you. But a is our initial value, some initial value, and then the exponential growth or decay is the e to the kt, where k is the constant that we're looking at, and t is the amount of time that has gone by. I'm going to try to put this all together. There's a lot of moving pieces in this problem before you get to the actual answer. And the question is, by what factor will the population have increased during the first 3 days? So we're looking for some multiplier, some factor that has changed the population over the first 3 days. So let's first use our initial condition to probably set up an initial equation. So our initial condition is that we know that we're starting with 15,000 for a population. So I'm going to write that down, that y is equal to 15,000 e to the kt. But remember that the initial condition takes place when t is equal to 0. So y is equal to 15,000 e to the k times 0. And k times 0 is 0, so we get y equals 15,000 e to the 0. And hopefully by this time of the year we all remember that e to the 0 is just 1, so y equals 15,000, which should make sense to you because we're saying that our initial condition at time 0 is that we're starting with 15,000 of something. So there's no change. It's just there's the population. There it is. We're not doing much to it. Now, the other piece of information that we're told is that the population is quadrupled during the first 2 days. So quadrupled means multiplied by 4. So our initial population of 15 is actually turned into 6,000 in the first 2 days, so when t is equal to 2. So let's maybe take a look at that, what that looks like. That, our quadrupled population of y is equal to 15,000, our initial value, e to the kt. And we know that this is when t is equal to 2. So 6,000 is equal to 1,500 e to the 2k. We would like to actually find what the value of k is for this scenario. So the first thing I'm going to do is divide each side by 1,500. Oddly enough, that's the exact opposite of what we did before. We multiplied 4 times 1,500 to get 6,000, so this is going to be 4 is equal to e to the 2k. And then to solve for k, I'm going to take the natural log of each side. And k is going to equal natural log of 4 over 2. Now, that is not the answer to the problem. I don't know if that was one of the multiple choice answers, but we're going to actually be answering a question about the first 3 days. This isn't information about the first 2 days. So we're going to have to skip screens here. I'll rewrite some stuff at the top and then rejoin you. Alright, so here's my initial equation again, and here's my k value of natural log 4 divided by 2. So let me just substitute that in. I'm looking at my initial condition of 1,500 e to the kt, where k is equal to natural log 4 over 2 times some amount of time. And the final piece of information that we're told is that we are looking at t equaling 3. So if I can find out how much y is at t equals 3, I can tell you how much it's changed since its initial inception at 1500. So I need to do 1500 e to the natural log of 4 over 2, not to 2, times 3. We got to solve for y. Alright, this is going to get just a tad bit trickier, so see if you can follow along. So 1500 stays 1500. E to the natural log of 4 divided by 2 times 3 is really e to the ln 4 over 2 to the third. Alright, now come over here for a sec. E to the ln 4 over 2 is really the square root of e to the natural log of 4. And e to the natural log of 4 is just 4. So that's the square root of 4, which is equal to 2. So I'm going to replace that and say that this is 1500 times 2 cubed. 2 cubed is 8. 8 times 1500 is 12,000. So that on the third day, we're looking at 12,000 bacteria. The question is, if that is the third day, so if 12,000 is the third day, what's the multiplier times the original condition of 1500 that got us there? Well, K is going to equal 12,000 over 1500. So 120 fifteenths, and actually 120 fifteenths is 8. So the question being, what was the multiplier, or by how much did it, what factor did it change? It changed by a factor of 8. All right, that's a difficult little problem that requires you to think back to Algebra 2 and then use some, we had some log rules in here that we had to use and some exponential stuff. So tricky little question, but definitely doable, even without a calculator.